Thank you for the introduction. So a lot of data from the real world can be naturally represented as tensors, which generalize matrices from linear algebra to have any number of dimensions, not just rows and columns. As an example, a data set of product reviews on Amazon can be represented as a three-dimensional tensor, as shown here, where each element encodes how many times a user uses a specific word to describe a specific product. And as we can see in this example, tensors that represent real-world data are often very sparse, meaning that most of their elements are zeros. And often, they're also much too large to be stored as dense tensors. And so many different data layouts or formats have been proposed for efficiently storing these kinds of sparse tensors. Now, these are just a few examples of the many different formats that have been proposed for storing a specific kind of sparse tensor, namely sparse matrices. But in fact, vectors are also just one-dimensional tensors, and there are several different formats for storing those as well. And similarly, there are many different formats for storing tensors that have more than 2 dimensions. Now, all of these different formats have practical applications, from thermal and mesh simulations to machine learning, image processing, and data analytics. And this is because each of these formats can offer performance benefits in real use cases depending on characteristics of the application and data. As an example, we looked at 3 matrices that have very different distributions of non-zero elements within the matrix. And these are similar to matrices that represent image stencils, web graphs, and block-sparse neural network layers. For each of these matrices, we measured the performance, the time it takes to compute sparse matrix vector multiplication with the matrix stored in various different formats. And as these results show, each of the 3 formats we evaluated can offer tangible performance benefits depending on the exact distribution of non-zeros within the matrix. And so what this demonstrates is that in order to maximize performance in general, we have to be able to efficiently compute with as many disparate formats as possible, not just 1 or 2. And so my name is Steven, and today I'd like to talk about how we can do exactly that by generalizing a tensor algebra compiler theory called TACO so that it's agnostic to any particular data layout. More specifically, we're able to accomplish this by developing an abstraction for tensor formats that neatly summarizes how they can be efficiently accessed. And with the aid of this abstraction, we can make the compiler reason about how to generate efficient code for a much wider range of formats without having to bake any of them directly into the code generator. But to see why we even need such a compiler in the first place, let's take a look at some of the formats that we saw earlier. And to keep things simple, let's first focus on how we can store 2-dimensional tensors or matrices like the one shown here. Now, the simplest way to store a tensor like this is to just store all of its elements contiguously in a dense array. And now the nice thing about this representation is that the positions of elements in the array implicitly encode their coordinates in the original tensor. So as long as we know the position of an element in the array, we can easily recover its coordinates. But not only that, this dense array representation also supports efficient random access. And what that means is that given the coordinates of an element in the tensor, we can easily find its corresponding position in the dense array by computing a simple strided formula. The downside with this format, though, is that it wastes a lot of memory storing 0 elements. So ideally, we'd like to simply omit storing the zeros. But the problem with doing this is that now the positions of the elements in the array no longer gives us the coordinates of the tensor elements. And so to recover this information, we need to somehow store it separately in some set of auxiliary data structures. And probably the most straightforward thing we can do is just explicitly store the coordinates of every non-zero element. And that's how the coordinate format works essentially. So given any element, we can get its coordinates in the original tensor by just loading them from the rows and columns arrays respectively. But actually, we can save even more memory if instead of explicitly storing every element's row coordinates, we just keep track of which range of element belongs to each row of the tensor. And that's the idea of the CSR format, as shown here. And this means we can, for instance, get all the elements of row 1 very efficiently by just querying the pos array. But the drawback with this format, though, is that now given any arbitrary element, finding out which row it belongs to can be very inefficient as it requires scanning over the pos array. And furthermore, neither this format nor the coordinate format that we saw earlier supports efficient random access. And so to efficiently compute even the same operation with all these different formats, we need very different code. As an example, consider this very simple expression that element-wise multiplies 2 tensors b and c. Now, if b is stored in the coordinate format, but c is stored as a dense array, then we can take advantage of the fact that dense arrays support efficient random access to perform this operation by iterating over elements in b and for each element, find its corresponding element in C. And this can be done with a single loop, as shown on the left here. We can apply the same high-level algorithm if B is instead stored in the CSR format, except now we need two nested loops that separately iterate over each dimension of the tensor. But if neither operand supports efficient random access, then instead we have to perform this computation by simultaneously iterating over both operands and essentially performing a two-way merge. And as we can see here, this requires code that's much more complicated and has very different structure from either of the two previous examples, because it essentially implements a completely different algorithm. And so we just need three very different kernels that implement the same simple operation for three different tensor formats. But as we ask support for even more tensor formats, more operands, or even more operations, the number of additional kernels that you need to support all these different cases as well quickly becomes much too large for all these kernels to be reasonably implemented by hand. And so that motivates a compiler approach that can instead automatically generate all these different kernels. And so now in the rest of this talk, I'll describe how our technique can abstractly represent disparate tensor formats and show how this abstraction enables our technique to automatically generate efficient code that computes with those formats. I'll then highlight some results from our evaluation. But first, to see how we can abstractly represent disparate tensor formats, let's take a look at an example of a three-dimensional sparse tensor stored in the format shown on the right here. Now, conceptually, this format simply stores each slice of the tensor as a matrix in the coordinate format. But what's important to note here, though, is that all these arrays can actually be grouped into data structures that each encodes a single dimension of the tensor. In particular, the first array here encodes the coordinates of each slice of the tensor as an implicit range from 0 to 3 exclusive. The next two arrays here, meanwhile, stores the row coordinates of each non-zero element in the tensor, as well as keeps track of which rows belongs to which slice of the tensor. And finally, the last array here stores the column coordinates of every non-zero element in the tensor. So rather than thinking about this tensor format as a monolithic structure, we can instead view it as a composition of what we refer to as level formats, like dense, compressed, and singleton, that each encodes a single dimension of a tensor. And in fact, we can actually take these same per dimension level formats and rearrange them to express other tensor formats. So consider this 3x4 matrix that we saw earlier. If we use the dense level format to store the row dimension and the compressed level format to store the column dimension, then what we obtain is actually just the same CSR representation of the matrix, which we've already seen earlier on. But if instead we use the compressed level format to store the row dimension and the singleton level format to store the column dimension, then now what we have is actually just the coordinate format representation of the same matrix. And so we've just seen how different level formats can be composed in different ways to express two different tensor formats, namely CSR and the coordinate matrix format. But again, we can actually compose these same level formats in much more complex ways in order to express formats for tensors that have any number of dimensions. And these include relatively simple ones like the coordinate format for three-dimensional tensors, but also more complicated ones like the most generic sparse tensor format, which stores tensor elements as sparse collections of dense blocks. We can also express structured matrix formats like BCSR and LPAC as formats for multidimensional tensors. And if we define additional level formats like hashed, ranged, and offset that use different data structures to store tensor dimensions, then we can express even more tensor formats like diet and hash map vectors, for instance. So as we can see, a wide range of tensor formats can in fact be expressed as compositions of level formats. And this is great because the Taco tensor algebra compiler theory we presented last year at UPSLA actually shows how to generate efficient code for computing arbitrary tensor algebra expressions with operands that are stored in any compositions of these sorts of level formats, with the caveat, though, that the level formats had to be either dense or compressed. And at a high level, Taco achieved this by generating code that iterates over the operands dimension by dimension. So to generate code that computes this tensor vector multiplication, for instance, Taco would first generate code to iterate over the slices of B, and then within that, generate code to iterate over every row within the slice of B. Then finally, Taco generate code to iterate over the columns of B, as well as axis to C at the same time. In this way, we reduce the problem of computing with different tensor formats to the problem of computing with different level formats instead. But again, as we saw earlier, efficient computing with different combinations of data structures can actually require very different algorithms. And since different level formats can use very different data structures, the approach that Taco took to tackle this problem was to essentially just explicitly hard code what it has to generate for every possible combination of distinct level formats, like these, for instance. The problem with such an exhaustive approach, though, is that it simply doesn't scale if you want to support more than one or two level formats, since the number of possible combinations actually grows exponentially in the number of supported level formats. The consequence of this was that Taco could support many variants of CSR, but not any sparse tensor format that uses a different data structure to store tensor dimensions, even when it's as simple as a coordinate format, for instance. And so to work around this combinatorial explosion, our technique instead performs code generation in two separate steps. Specifically, given some computation on any combination of level formats, the compiler will first construct the most efficient high-level algorithm possible for performing the computation, based entirely on what high-level operations on tensor dimensions are supported by these level formats. Then the compiler will specialize the constructed algorithm so that it can actually compute with the specified level formats by taking into account how they implement the high-level operations that they support. Now, by separating code generation into these two separate steps, we can effectively untangle the problem of how to efficiently compute with different data structures from the problem of how to efficiently compute with multiple operands. And in this way, we eliminate the combinatorial explosion, and this makes it possible to generate efficient code for a wide range of different formats. Now, to see how this works more concretely, again, let's suppose we want to element-wise multiply two tensors B and C. And as we saw before, this requires the compiler to generate code that efficiently multiplies any row B with its corresponding row in C. Now, one high-level algorithm for performing this computation is to simultaneously iterate over both B and C and essentially perform a two-way merge to find all pairs of non-zero elements that share the same coordinates. Another algorithm, though, is to just iterate over all non-zero elements of B, and for each non-zero element in B, find its corresponding element in C. And now the second approach can be more efficient in general, since it only has to iterate over all non-zeros of one operand, as opposed to all non-zero elements of both operands. But this does assume that we can actually efficiently random access into C. So to be able to reason about which of these two algorithms the generated code should actually use, the compiler needs to know which of any of these operands supports efficient random access. And our solution to this problem is to simply have level formats explicitly declare whether they support efficient random access. And this is done through an abstract interface with design that's fixed across all level formats, and that exposes which high-level operations are supported by each level format. So for instance, the dense level format can be random accessed in constant time by simply computing a strided formula. But the hash level format, which uses the hash table to store tensor coordinates, can also be random accessed very efficiently by computing a simple hash function. So both of these level formats will declare through the abstract interface that they support efficient random access. On the other hand, the other four level formats don't support efficient random access, and they'll also declare that accordingly. And in a similar vein, we have every level format declare through this same abstract interface whether they support other high-level operations like efficient iteration and modification, which we talk about more in our paper. Now, knowing what high-level operations are supported by each level format, the compiler has everything it needs to know to construct the most efficient high-level algorithm to element-wise multiply B and C. So let's say B is stored in the compressed level format and C is stored in the hash level format. By creating the hash level format through our abstract interface, the compiler can infer that C can be efficiently random accessed since it's stored in a level format that supports efficient random access. And so the compiler can thus conclude that the computation can be more efficiently performed by constructing an algorithm that iterates over B and random accesses into C. On the other hand, if C is instead stored in the singleton level format, then by the same reasoning, the compiler can now infer that neither operand can be efficiently random accessed, and thus the compiler has to construct an algorithm that instead simultaneously iterates over B and C. And so the result of this process is a high-level algorithm that performs the desired computation, expressed entirely in terms of high-level operations on tensor dimensions as opposed to level formats. But now to get code that can actually compute with level formats, the compiler has to replace every high-level operation in this constructed algorithm with code that actually implements the operation. And again, our approach is to simply have level formats explicitly specify how these replacements can be done. So for instance, earlier we asserted that the dense level format supports efficient random access by computing a simple strided formula. So now we actually have the dense level format provide this code for computing the strided formula. Similarly, the hash level format will provide code that implements efficient random access by querying a hash table to search for stored tensor coordinates. And all these level formats will also provide code that's required to implement efficient iteration. Now, knowing how level formats actually implement the operations they do support, the compiler can very mechanically translate any high-level algorithm that it constructs to code that actually computes with specific level formats through a very simple inlining process. So again, going back to our element-wise multiplication example, earlier we saw that when C is stored in the hash level format, we can compute this operation by iterating over elements in B and random accessing into C. Now, since B is stored in the compressed level format, we can replace this high-level operation here that iterates over elements in B with code that instead iterates over the compressed level format. And similarly, because C is stored in the hash level format, we can replace this high-level operation that random accesses into C with code that instead random accesses into a hash level format. And now what we're left with is code that efficiently computes element-wise multiplication with the compressed and hash level formats. And so that shows how we can generate efficient code to compute with any combination of level formats. And again, we can apply this technique dimension by dimension to get code that computes on tensors with any number of dimensions. And as we can see here, such code can iterate over and access the various dimensions of the operands in very complex interleaved ways, which makes the code very difficult to write by hand. So that's a brief summary of our technique. Now to evaluate it, we implemented it as a prototype extension to the Taco tensor algebra library. And we evaluated it both against Taco without our extension, as well as against various widely used sparse linear and tensor algebra libraries. For each of these libraries, we looked at which tensor formats it supports, and what we found was that all the libraries support only a handful of formats each, with some like TensorFlow, for instance, being particularly limited in terms of the what formats they support. And this reflects the fact that it requires a lot of effort to manually implement all the kernels that would be needed to fully support many disparate formats. Now, Taco, without our extension, could instead generate these kernels, but only for what are essentially variants of the CSR format, and not for any format that uses different data structures to store sparse dimensions. Our technique, by contrast, can generate code for most of the tensor formats we looked at, and can support even more if we define additional level formats on top of the 6 that we saw earlier. But not only that, our technique can actually generate efficient code to compute with all these different formats. To demonstrate this, we evaluated a wide range of tensor algebra operations on disparate formats, from simpler ones like sparse matrix vector multiplication with coordinate format and die matrices, to more complex ones like CSR matrix addition and the compound coordinate MPT-KRP kernel. This last kernel in particular multiplies a 3-dimensional tensor by 2 matrices and is a key operation in many data analytics applications. Now, for each of these operations, we measured the performance of sequential code that our technique generates and compared it against those of equivalent handwritten kernels that are implemented in these other libraries. Specifically, the results here show the geometric means of normalized execution times across a set of test tensors, so the lower the better. And what we found was that on the whole, our technique does in fact generate code that has comparable, if not better performance than other libraries. Sometimes much better, in fact, since our technique can always generate code that's specialized to the input data structures. So, in summary, by decoupling the problem of how to compute with different data structures from the problem of how to compute with multiple operands, we can automatically generate code that's needed to efficiently compute with tensors that are stored in a wide range of disparate formats. And our approach makes it easy to add support for even more tensor formats, including even custom ones, by just composing existing level formats in new ways and or defining new level formats, which can be done both easily and incrementally. And so this makes it possible to get good performance across a wide range of tensor algebra applications in disparate domains. So we'll be releasing an implementation of our technique in the publicly available version of Taco in the coming weeks. For now, though, I'll conclude my talk, and I'll be happy to take any questions. Thank you.
So can you talk a little bit about result allocation? I noticed that in particular you have things like sparse CSR addition in this, and that runs into the problem that in general you don't know how big your result is going to be or where it's going to go. How do you deal with that in your system?
Sorry, can you repeat the question? I didn't quite.
How do you deal with result allocation? Where do your results go, and how do you know that you have enough space for them?
Right. So all that's so again, we model modifications on these data structures for storing sparse dimensions as these high-level operations that are hidden from the compiler. So to generate these high-level algorithms, it doesn't reason how to do the allocations, and that's all done by implementations of these high-level operations. So that's essentially, if we go back to this example, right? So, sorry. So yeah, so in a similar way, we implement code to modify the data structures as these sort of as like implementations of high-level operations that correspond to modifications of the data structures. So that's all taken care of by these implementations, and that can be optimized by us as developers of the Taka library, or as by users of the library if they define custom formats. Yeah.
Gregor, can I ask you a quick question?
So the art of choosing which format you should use in the first place is pretty complicated, and it seems like this is sort of notionally reversible in that you could say, hey, I could have made this much faster if you had chosen these formats instead of these formats. Have you thought about that? Have you thought about that sort of communication back to the designer of, gee, I chose poor performance here because of the encodings you used. Maybe you should use this instead.
Right. So this doesn't give feedback as to why a particular format does well or poorly. But yeah, it is interesting, like the problem of which format to choose for specific operations or even specific kinds of data is an interesting problem. And yeah, so this technique basically assumes that given some decision as to what formats to use, what's the best way to work with those formats. And on top of that, we can imagine building a system that, like an autotuner, for instance, that can try out these different possible combinations and evaluate them to see which is the best format. Yeah, and that could be built on top of such a system.
Great. Thanks.
You want to use
Yeah, sure.